In this section, we're going to look at a technique of integration called the substitution rule. If we think back as to where we are right now, we just introduced the definite integral, and that was in relation to the area problem. And then we found this connection between the definite integral and the antiderivative of the integrand. So there was this intimate connection between integration and antidifferentiation. So what that in turn told us was that if we want to work out integrals of functions, then perhaps we should start by looking to see if we can find an antiderivative of the integrand. Now, in Calculus 1, we saw that there was many ways to take a derivative, depending on whether the function was a product of two things, or a quotient of two things, or a composition of two things. We had all of these differentiation techniques. If it was a composition of two functions, then we took the derivative by using the chain rule. Similarly for products and quotients, we had the product rule and the quotient rule. Now, if we're doing everything backwards now, based on the fundamental theorem of calculus, to do an integral, we need to find an antiderivative. So essentially, we need to do all of those things we did in Calculus 1 backwards. It means we need techniques to figure out, okay, am I staring at something that came about as the derivative from a composition using the chain rule, or a product rule, or a quotient rule? Well, the substitution rule here can be thought of in some sense as undoing the chain rule. So let's just recall what the chain rule for differentiation said. If we want to compute the derivative of a composition of two functions, f composed of g of x, then we take the derivative of the outside function, evaluate it at the inside function, and multiply by the derivative of the inside function. For us, it'll be convenient just to express this in terms of differentials. So if we let y be f of g of x, then the differential dy is just the derivative of the function times dx, and we just wrote what the derivative was above using the chain rule, g prime of x dx. Okay, so there's an expression of the chain rule written in the form of differentials. Now, the thing that we're interested in is trying to figure out if our integrands look like this piece on the right-hand side. Because if our integrand looks like a piece on the right-hand side here, then we know it had to come from the derivative of some composition using a chain rule. So our goal is to try to figure out if we can stare at the integrand and pick off some function g where its derivative also appears. So does this appear? For some function g, part of the integrand, does its derivative also appear? And if it does, it means that the integrand is really the derivative of something coming from the chain rule, so some composition, and so that'll give us a bit of help in order to figure out what the antiderivative has to be. So let's look at an example of this. What if we think of dx as the differential, so much as what we did over here, and consider taking u to be e to the negative x squared. That is, pick a piece of the integrand and just let that be u. And now if we look at the differential, so differentiating this thing on the right is the chain rule, so it's e to the negative x squared times the derivative of the exponent, which is negative 2x, and that's dx. And what we notice is that this is actually the entire integrand, along with the dx there. So we've just seen that this integral that we're trying to deal with is equivalent, in terms of this new variable u, of just the integral of 1 du. Right? We've just replaced everything on the right-hand side here with what it is in terms of the new variable u. And this new integral is something that we can easily work out. It's an integral of 1 with respect to u, so the antiderivative of 1 is just u, plus our arbitrary constant of integration. And now we can re-express everything back in terms of x again. And so this was e to the negative x squared plus c. And so there is our antiderivative of our integrand. Let's check this to make sure. In order to check, and I recommend you do this every time you compute an antiderivative, just do a quick check to make sure that you did get an antiderivative. You didn't make any mistakes. Differentiating this thing, chain rule, negative 2x e to the negative x squared, and that's exactly the integrand. Of course, this derivative computation is exactly the one we did above. So we've got our antiderivative. And let's just recap how we did this. We looked at the original integrand, and we perhaps thought to ourselves, hey, this is not that straightforward. I can't really spot what function has that as its derivative. But I can perhaps simplify things. Maybe it's coming from the derivative of composition, and so I'm going to try to simplify things by looking in the integrand and seeing if I can replace some part of it with a variable u. And the only way that will be successful is if, when I replace some part of it with the variable u, the derivative of u also appears in the integrand as well. And it just happened to be the whole thing. So we replaced it, wrote it in terms of a new variable, wrote the integral in terms of a new variable, and we managed to solve that. This is essentially the fundamental rule of problem solving, is if you don't know how to solve a problem, try to convert it to a simpler one. And we're doing this conversion to a simpler problem by replacing some complicated piece of the integrand by a variable, and we hope that that will simplify the integrand down to something that's easier to work out. So here's the general statement of the substitution rule. It says that if u is a function g and it's differentiable and the range is an interval I on which f is continuous, then we have the equality of these two indefinite integrals. The hypothesis here is just to make sure that the integrals in question below actually exist. And what this is really saying is that if we stare at an integral where the integrand has the function g appearing and its derivative appearing as well, then it's possible to simplify this integral down to an integral involving just the outside function f alone. The idea of doing the simplification is to just realize that, hey, wait a minute, this looks like the derivative of a composition of two functions coming from the chain rule. And if I can pick off what the inside function is, namely g, that's what I'm going to substitute for, if I can spot that in there, then the antiderivative computation really just needs to focus on what the antiderivative of the outside function is. In the next few slides, we're going to go through a number of examples of this, so we'll get lots and lots of practice with doing this. So the slides for the next few items are found in the links in the description below this video. Each item in the notes has a number beside it, and I've just broken up the subsequent videos for this section based on item number. So if there's a particular item you want to see done right away, maybe it's an example or something, you can just click the corresponding link below. They're all done in order, but you can also quickly navigate to the ones you want to see. All right, have fun.